Good morning, everyone. It's my great pleasure to share this session this morning and to introduce my old friend, my long-time friend, that way, to the Zamfirescu, who will speak about cheap cages. And depending on how cheap they are, we may all consider buying one and then selling it later at a much higher price.
I don't know. Thank you very much for the introduction. I don't know if you can sell it at higher price than what I am selling it. So, cheap cages. Thank you very much for inviting me here to this conference. And of course, it's an honor for me to be here and celebrating three very old friends. Very old, from the 60s. From the 60s. I think first time when we met was 68 or 69 or something like 68 maybe. Excuse me for sitting, but I am old. Yeah. And I am not only old, but I have a problem with my back because there are older people who have not such problems. Fortunately, they have other problems. So. Cheap cages means, in fact, of course, if you take them in gold, they will not be cheap, normal, except if they are very small. But we want to see something, we want to put something in the cages so they can't be very small, and it doesn't matter which material. They are cheaper if they are shorter, normally, naturally. Short means, but what is a cage? A cage is one skeleton of a convex polytope. We will work only in R3. Okay? So this is a cage. In R3, one skeleton of a convex polytope. And the length is the total length of the edges of this skeleton. So far, nothing new. Cooperation Augustin Frouchard. So I said already what is the cage. What I want to hold in the cage. There will be compact convex sets. Maybe I will call them convex bodies. Usually the convex bodies are full dimensional, but in this case they are not. Many of them are not. They are 2 or 3 dimensional compact convex sets. The question of finding the length, minimal length of a cage holding the ball is old. The origins are from the 50s, when Coxeter raised this problem, finding a cage holding the ball, the unit ball. I will come back on this problem and the solution a bit later. Bezikovic and Eberth solved it. Bezikovic gave an example, and Eberth showed that it is optimal. What means holding? It's easy, even the mathematical, but it's easier. Well, it's easier just to take it intuitively. It is inside, cannot go out by a continuous movement. That's it. Yeah? If something is unclear, please ask me, because I think everything should be clear. Unfortunately, this talk will be different from other talks I held in my long life so far. Namely, it will be more technical. Usually I present just some nice pictures, and well, this time it will be a little different because we need techniques, we need machinery to solve what we have to solve. We want, especially, first of all, we focused on small cages, short cages, holding two-dimensional controls, so like a disk, for example, two-dimensional disk. It may appear to be trivial, it is not trivial. It is trivial to find a cage, but it is not so trivial to find that what is the minimum, the infimum we can badly speak about minimum, infimum of the length of the cages holding a unit disk. And other guys like this we want to do. So let's start with this notation. Lambda is one-dimensional, as you see. This will be simply the convex hull, x1, xn. It's simpler to write like this. And you see this second definition, which is the length of the boundary of the convex hull of the endpoints. In particular, this is that. As there is a related notion of perimeter function, which is almost, sometimes it's exactly the same as this one here, but not always it's the same. You see that here is no. Yeah, it's written. If x1, xn are coplanar and in convex position, and which means I want to say x1, xn is an odd-degenerate convex angle with consecutive vertices x1, xn, then this means the same as this, except for the case that they are collinear. If the endpoints are collinear, for example, if there are just two of them, then it is a double, the perimeter. Well, it's a small difference, but we use both. So, and now this is the goal of our research, namely to find the infimum of all lambda g being the length of the cage G over all cages which hold the compact convex set K. And we are looking for L of K, as I said before. This is the infimum of all cage lengths. This function is upper semi-continuous, but not continuous. It is not too difficult to see that it is not continuous. However, you will probably not be able to see it immediately. It follows from some theorems which are coming. If you take a square, but I give you the example. If you take a square, so two-dimensional compact convex set, I will, I don't know, and approximate it by taking here a point converging to this vertex on the edge, on the very edge, and this goes to this vertex. All the way, this is different from this, and there's a gap, and the limit is not the number which corresponds to the square. Now, one of the tools, unfortunately, we needed to go ahead was this pair, G eta. G being a graph, and eta an embedding of the graph in a plane. I suggest you can see then the constraints which define this pair, the geometric graph. You can have a look. And I suggest you imagine G to be the cage, the plane to be some plane, any plane, and eta be a projection, orthogonal projection, for example. Orthogonal projection onto that plane. Because this is the way we will use this geometric graph. So this means every vertex projects to a point on the plane, it's normal, and for any edge, the eta goes also onto a line segment in the plane, exactly like in the case I was mentioning. The projection on a plane of the cage. This is where we applied. The whole thing, projection of G, is eta of G, which is set in pi. And this is true, what I wrote here, obviously, if you take the projection, but this is... yeah. Now, a vertex of the cage, I will take G to be the cage already, is called external if the projection is of the boundary of the convex hull of the whole projection. And an edge is external if the same happens, the edge projects into the boundary of the convex hull of eta of G. External vertex and edge. And now we ask these things, that for any point in the plane, the pre-image is not more than 2. Pre-image concerning only the restriction to the vertices. Not more than 2 vertices. This is true for a cage, because a cage is one skeleton of a polytope. So it cannot be that you have 3 points or one over the other to project on the same point. Generally speaking, it may. So if this happens, and this is even more important, for any side of the convex polygon, which is the convex hull of eta of G, what is down here on the projection on the plane, there is at least one path CG such that, look, you have the projection, you have a side of this polygon. There might be more than one path projecting onto this, but not more than 2. Again, because of the convexity of the polytope of which the cage is one skeleton. So this is the second, you see, there is at least one path such that this, here is not written that there are not more than one, but it follows from the first condition. Anyway, this is, you have at least one, PS. This one of them is called PS. And then the geometric graph is called convex. Now we do this. We delete from the cage the edges of PS. PS is one of those paths which projected on a side of the polygon of the projection. One of them, only one. Of one of them I take, if there is just one, I take it out. So we delete from G the edges of PS, of each time of one of such, of these paths. To obtain this graph, nabla G. This is a graph of which several edges were deleted. And, this is a strong connectivity of G. This is a standard thing. Now, this is important that if we have such a graph G eta, which is convex, has these properties and strongly connected, then nabla G is connected. This is essential for what is going to come. Nabla G, what remains is connected. If G eta is strongly connected, it's something which happens for our cages because of the 3 connectivity of that graph G is 3 connected. Because we know this very well. So if the geometric graph is convex and strongly connected, then nabla G is connected. Nabla G is what remains after deleting those edges which project, roughly speaking, on the boundary. And now define the length of this geometric graph. The length of this geometric graph is the length of the projection of nabla, so G minus those deleted edges, and the boundary, the length of the boundary, down. You see that sometimes where there were 2 paths, one was deleted but the other one not. So you still keep that one, and you add now the whole boundary here. It is important if you think of the projection, but it's difficult to understand well what I'm telling you here before you see the proof. And you did not yet see the proof, and you are not going to see the proof because it's too I have not the time to go into proofs usually, almost never. So S of V1, Vn is the length of the shortest active area. So the length of the Steiner tree associated to those points. The length. And let's add the perimeter to S and get a function f. So the function f is, roughly speaking, the perimeter for points. Now here the points are in R3, but they will be used mainly on a plane. So in a plane we have f to be the perimeter of the polygon and plus the Steiner tree, the length of the Steiner tree defined by the vertices. You see. And this is almost the same. It is exactly the same if n is at least 3 and the points are coplanar in convex position in the plane. F of V1, V2, if you have just 2 points, is 3 times the distance because P is already twice and the other one is 1. Now, we go now to this corollary is clear. Why is clear? Because the length of the geometric graph, as it was defined, you remember, is this. This is by definition, the first line here. Is at least this plus that, because the first one is the length of the projection of nabla. As it was defined, nabla, this must be greater or equal to S of eta of those projections. And the other one is P, perimeter, which is exactly the definition of F. So this is immediately as a corollary we get. This is elementary. If the function phi is 1 Lipschitz, then we have that and we have that and we have that. We see immediately that they only decrease. It's not like the problem with the disks. Theorem, another theorem. Now we arrive to the moment of applying that, what we did before. We have a cage, we have some plane, and if V1, Vn are the external vertices of the projection of G on the plane P, such that these lie in this order, on this, then we have the length of G of the cage, at least f of this. This will be crucial for the calculations afterwards. Proof. Indeed, this is now not so difficult to prove because, well, the first part is about connectedness. This is even easier. Then the geometric graph is stronger. Also, it is easy to verify that this is convex. You can believe this is. Now, G is nabla plus the union of the PS. Because if you add to nabla G all this PS, you get back to G, because this was to get nabla, you just took out the edges of PS. So lambda G, the length of G, is the length of nabla G plus the sum of all these. And now we just use what we got before. And we have lambda G at least this, because of that. And this is at least that, which is at least that. This we did before. Yeah. So now we have a connection between the length of G and this function f. But we have to investigate a little the function f. And S also, the length of the, I don't know how well known is this, but if you have endpoints in the plane, and you have 3 points in their convex hull, then S of ABC, the length of the Steiner tree defined by ABC, is smaller or equal to S of V1, Vn. It seems trivial. It is not difficult to prove this. And also the other one, this is even easier. But what is interesting? This is interesting. This is interesting. One could expect that this happens always if you have a fewer points in the convex hull of more points, that S of M less or equal. This is not true. This is already for M equals 4, not true. And this can be seen, I will skip this part because I explain here, it's easier to see on a figure. If you take those many points close to A, B, and C, this is an equilateral triangle, close such that here a couple of them, and here, and there, so that ABC is inside the convex hull. Then taking 4 points in the convex hull, A, B, C, and A4, A1, A2, A3, and A4, will give you a longer Steiner tree. That's easy to see because those many points close to A, B, and C give, in fact, in the limit, the length of the Steiner tree of ABC, which is square root of 3. No, because you add these 3 things and you get square root of 3. But if you take the 4th point here, this is longer. Of course, it's longer. I don't need to. It's calculated. It is here, but it is here. It is this number, half of 1 plus square root of 7, which is more than square root of 3. But it is also clear because it is not the Steiner tree, this one here. And the Steiner tree is a minimum, and this is only one minimum. So this is more than that. Huh?
So you add points and the Steiner tree gets shorter?
I add points to what?
And vertices to those 4?
No, this is not conjecture, but what could expect is that if we have a few points inside the convex hull of many points, that the Steiner tree of the fewer points is shorter than the Steiner tree of the many points. And here is a proof that this is not the case. No, it's not. It is only in the... No. It was not said that the points are among those. No. In the convex hull. You see, that the convex hull, V1, Vn, is the convex hull, is not the set. Otherwise, it would be trivially wrong. Yeah. Yeah. But this is true for 3 points. For 3 points. M is 3. For m equals to 3, this is true. But for already 4 is not true. This is what is shown here. Now, again, it's perhaps better to see a figure. There is a figure, not a very successful figure, but still better than nothing, to explain this theorem. You see, first of all, let's read here. We have a planar convex body, and we have assumed there's a Steiner tree determined by 3 points on the boundary, and it has a vertex V inside. Steiner tree has already minimality. If f attains a local minimum at x, y, z, then we have this, and we have this figure. But here in this figure, please think that these are orthogonal to this, and that to that, and that to that. I don't know how we came up to this wrong figure. But this you have to think they are orthogonal, because this is what happens. These must be orthogonal. This is a conclusion of the theorem. Must be orthogonal, and also the angles alpha x you see here, and beta and gamma correspondingly. Alpha x and alpha y and alpha z. And we have accordingly beta x, y, and z, and gamma x, y, and z. They satisfy this. Okay. So this is a lemma. This is used at some point. We have this now, a lemma here. I don't prove this here. That's the infimum of f when x, y, and z are on the unit circle, and 0 is inside the convex hull of x, y, and z, is 6. This is easy to see, very easy to see, that this is 6. If you take the points and you play a little bit with them, you'll see that the minimum is the infimum, the minimum is when they collapse into two of them in one point and the other is antipodal. And then the sum is 6. So if ABC is an equilateral, now I go ahead to try to find the L for planar convex bodies. This is a step towards finding L of S1. L of not F, S1 of the unit disk. S1 is a circle. So lemma 5 is ABC is an equilateral triangle of sides and side lengths delta. Then the infimum of F when the points U1, U2, U3 run on the various sides is that number. And this infimum is reached precisely at the midpoints of the three sides of the equilateral triangle. Something similar for a parallelogram. A parallelogram with diagonals small delta, one diagonal, smaller diagonal, small delta, has this infimum 3 delta. The infimum is taken over 4 points running over the 4 sides. Yeah, the infimum is reached precisely at its two opposite vertices. And if it is a triangle, you have, of course, 2 such positions. Now, we are still far away from the goal because we have only some results from one side concerning L. Now about the other side, and we need another tool. First, a remark. In the sense of bare categories, we have this, that most convex bodies touch the inscribed circle in exactly 3 points, and of course the origin, if the origin is centered, is the center of the circle, is inside the interior of ABC. In such a case, which is the typical case, the points ABC fix the convex body. The convex body is planar. Yeah. But there are convex bodies which can't be fixed by any set of 3 points. For example, parallelograms. We define the notion of almost fixing. Several points A1, AN are in the boundary of a convex body, planar convex body. Almost fix that body if there are pairs of points as close as you want to the previous ones, pairs. One point has a pair, one left and one right. The second has a pair, and so on, so that all these 2n points really fix k. So then we say that a1 up to an almost fix k. And we can prove that for any planar convex body, there are 2 or 3 points almost fixing k. You can say there are always 3, but there's many, often there are 2 only. Now, we want to progress concerning L. I don't think that, well, cages for planar convex bodies in space, but we start with planar convex bodies, yes. Right, planar convex bodies. Rk should be the inner radius of the planar convex body K. Okay, then the theorem says, one theorem says, we have that L of K is at least 6R of K. Next theorem, let K be a planar convex body in R3, but again planar, and ABC be in the boundary. Then, if 2 of them almost fix K, then L of K is smaller or equal to F of A and B. And the same with 3 points. If A, B, C almost fix, you know that there are 2 or 3 almost fixing. Then we have these inequalities. However, we can't yet answer this question here. Next. We say that a convex body is weakly strictly convex if it possesses 2 parallel supporting hyperplanes at distance width of K. So you take the width, take those 2, there must be 2 supporting hyperplanes at distance width of K. And then if one of them has just a point of contact with the body, it's enough for me to say it is weakly strictly convex. So it doesn't matter what happens in the other place. So it is a very weak notion, requirement. For any planar weakly strictly convex body, we have L of K smaller or equal to 3 times the width of K. So corollary to theorem 6. We have another corollary. If K contains a disk of diameter width of K, this is not guaranteed, but if it is the case, then we have that L of K is exactly 3 times the width of K. And this solves the problem for the unit 2-dimensional disk, because the unit 2-dimensional disk satisfies this condition. So we have that L of D is indeed exactly 6. We have this inequality, but we had also the other inequalities, you see, greater or equal to 6R, you see. From these 2 inequalities, you get the equality here. What? Sorry?
What does the K look like?
For the disk is, if I remember well, is the cage is on one side. It is the cage is made up of a Steiner tree and a triangle, and the Steiner tree is on one side and the triangle on the other side, both very close to the plane of the disk, to the disk. Yeah, tetrahedron, right. It is not difficult to guess this, but to prove that this is indeed the infimum. Got in this way, you need quite a lot of machinery. Unfortunately, we could not solve it more easier. Of course, the machinery is good for other purposes too. But the machinery already we presented. So. Yeah, but it is you have but 6 because the unit radius is 1. Then you have 0. 1 is close to 0. 2 are 2, and this is 1. So they are very thin. It's very thin, and here is 2 here, 2 here, and 2 here. 2. You see, it's a thin tetrahedron. This is an infimum. So these tetrahedral cages hold the disk. This was immediately seen at the very beginning, but not that this is optimal. Now, if T is a triangle of sides, of these sides, then we have L of T equals to minimum of this. And in particular for the equilateral triangle, we have calculated exactly L of T is this. Each of these things has a proof which is sometimes not short, but not very difficult. If K is a parallelogram with diagonal lengths delta small delta, big delta, smaller delta being at most equal to big delta, then we have this. L of K at least 3 delta. And if K is acute, what means acute? Acute means that diagonals divide the angles wherever into 2 acute angles. If this is the case, then we have exactly 3 delta, small delta. And in particular for the unit square, where the condition of acuteness is satisfied, we have 3 square root of 2. Because delta is square root of 2. And now we go to cages for convex bodies in space, in 3-dimensional space. So 3-dimensional convex bodies. And remember first the result of Bezikovich and Ebers. Bezikovich gave the solution, the example, and Ebers showed optimality. Ebers' proof was extremely long. It is an old result. I'm sorry that I did not put here the year, but this must be in the 60s or 50s, 60s. Theorem 8 gives a general bound, upper bound, because it's quite difficult to give anything better than an estimate if you don't know anything about the convex body. And here we know nothing. So we have this bound here. First, smaller or equal to 2 pi diameter of K, and then if it is strictly convex, we can improve into this. For the regular tetrahedron of unit edge lengths, we have what you see here. The proof here is again maybe 2 pages long, but I don't present it, even if I could have time. I don't really have time, but I anyway cannot give you the proof. And now this is the last thing. For the cube, this I will present as a problem this afternoon. For the cube of unit edge length, we have this. L is at most 4 plus 3 square root of 2. How is the here, this is made this the following way. This ape, these things, you have nothing. Here are small, but also this is small. So this can be done very small. This is small and this is small. And so that this is going below the cube, and this is, you see. So that in limit, we have 3 times the diagonal and 4 times the edge, which means 4 plus 3 times square root of 2. But we are far away from being able to prove this, that this is optimal. We've found it, but the optimality is, I don't know which methods should be. Maybe, but this I give you as a problem. It's the best thing to do. Thank you very much for your attention.